Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. 4.5 billion years ago, a catastrophic collision occurred that would forever change our cosmic neighborhood. A Mars-sized protoplanet called Theia slammed into the early Earth, ejecting a massive cloud of debris that eventually coalesced to form what we now know as the Moon. This violent beginning marked the start of a fascinating and ongoing celestial ballet, one that continues to this day, right above our heads, yet remains largely unnoticed by most of Earth's inhabitants. The Moon, our planet's only natural satellite, appears to be a constant companion in our night sky. But appearances can be deceiving. With each passing year, our lunar neighbor drifts approximately 3.8 centimeters farther away from Earth. This phenomenon, known as lunar recession, means that the Moon is, in essence, slowly escaping Earth's gravitational embrace. To understand this cosmic drift, we need to dive into the complex physics of orbital mechanics and tidal forces, the same forces that create the rhythmic rise and fall of ocean tides that have shaped human civilization for millennia. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The story of the Moon's gradual retreat begins with an understanding of tidal friction. Earth's rotation takes 24 hours, while the Moon orbits our planet once every 27.3 days. This difference creates a fascinating dynamic. As Earth spins faster than the Moon orbits, our planet's oceans form a tidal bulge that actually pulls ahead of the Moon's position. This misalignment creates a gravitational tug-of-war. The Moon pulls back on this bulge, effectively slowing Earth's rotation by about 2 milliseconds per century. Meanwhile, Earth's gravity pulls forward on the Moon, transferring angular momentum and boosting the Moon into a slightly higher orbit. This orbital boost is what causes the Moon to drift away at its current rate. Scientists have confirmed this recession using an elegant technique developed during the Apollo missions of the 1960s and 1970s. During Apollo 11, 12, 14, 15, and 16, astronauts placed retroreflector arrays on the lunar surface, essentially sophisticated mirrors that allow researchers to measure the exact Earth-Moon distance with extraordinary precision. By shooting laser beams from observatories on Earth to these reflectors and measuring the time it takes for the light to return, scientists can calculate the distance with an accuracy of just a few centimeters. The Lunar Laser Ranging Experiment, as it's called, has provided over 5 decades of data, confirming the Moon's steady retreat. The implications of this celestial distancing are profound and far-reaching. Earth's day is getting longer. The Moon appears slightly smaller in our sky than it did for our ancestors. And given enough time, billions of years, this continuing process will significantly alter the rhythms of our planet. What's particularly fascinating is that evidence of the Moon's recession isn't limited to modern laser measurements. Earth's rotation has been slowing throughout geological history, and this is recorded in the daily growth patterns of ancient corals and bivalve shells. By counting growth rings in fossils, scientists can determine the number of days in a year, during different geological periods, providing a natural archive of Earth's rotational history. The physical mechanism driving the Moon's retreat involves a principle fundamental to physics, the conservation of angular momentum. Angular momentum, the rotational equivalent of linear momentum, remains constant in a closed system, meaning it can transfer between objects but cannot be created or destroyed. This principle governs the cosmic dance between Earth and Moon. As Earth rotates, its tidal bulges, caused primarily in the oceans but also occurring in the solid Earth, are pulled slightly ahead of the Moon's position by the planet's rotation. These bulges exert a gravitational torque on the Moon, accelerating it forward in its orbit. In response, the Moon moves slightly farther from Earth to conserve the system's total angular momentum. Simultaneously, the Moon's gravity pulls back on these tidal bulges, creating a drag that gradually slows Earth's rotation. This transfer of angular momentum from Earth's spin to the Moon's orbital motion is the key mechanism behind lunar recession. Earth loses rotational energy, and the Moon gains orbital energy. The mathematics describing this process were first formulated by George Darwin, son of Charles Darwin, in the late 19th century. His work provided the theoretical foundation for understanding tidal evolution in the Earth-Moon system, predicting a recession rate remarkably close to what modern measurements have confirmed. Tidal friction also manifests in the rhythmic ocean tides experienced on Earth. The gravitational pull of the Moon creates two bulges in Earth's oceans, one directly beneath the Moon and another on the opposite side of the planet. As Earth rotates, land masses move through these bulges, experiencing high and low tides. The Moon's gravitational pull drags these bulges slightly ahead of the direct Earth-Moon line, creating a time lag between the Moon's position and the corresponding tidal bulge. This asymmetry generates torque that transfers energy and angular momentum from Earth's rotation to the Moon's orbit. When Apollo astronauts deployed the first retroreflectors on the lunar surface during Apollo 11 in 1969, they couldn't have anticipated how these simple devices would revolutionize our understanding of the Earth-Moon relationship. The Lunar Laser Ranging Experiment uses these reflectors to bounce laser pulses off the Moon's surface. By precisely timing how long it takes for the light to make the round trip, scientists can measure the Earth-Moon distance with millimeter-level precision. These measurements have confirmed that the Moon recedes at an average rate of 3.8 centimeters per year. However, this rate isn't constant. It varies with factors like the configuration of Earth's continents, which affects oceanic tidal resonances. During periods when the continental arrangement creates larger tidal ranges, the recession rate increases. The physics of this process creates fascinating feedback loops. As the Moon recedes, its apparent size in our sky gradually decreases. Currently, the Moon's distance allows it to almost perfectly cover the Sun during total solar eclipses, a cosmic coincidence that has profound scientific and cultural significance. Eventually, in the far future, the Moon will appear too small to completely cover the Sun, and total solar eclipses will no longer occur on Earth. Earth's rotation continues to slow due to this tidal friction, adding about 1.7 milliseconds to the length of our day every century. While imperceptible on human timescales, this has cumulative effects. During the time of the dinosaurs, approximately 100 million years ago, a day was roughly 30 minutes shorter than it is today. Written in the geological record of our planet are subtle but undeniable clues about the Moon's historical dance with Earth. Among the most compelling evidence comes from an unexpected source: fossilized corals and bivalves. These marine organisms record daily and seasonal growth patterns in their structures, creating natural chronometers that scientists can read to determine ancient day lengths. When paleontologists examine a 400-million-year-old coral fossil, they can count the number of daily growth ridges between annual bands. These counts reveal that during the Devonian period, Earth's year consisted of approximately 410 days, each lasting about 21.3 hours. This striking difference from our modern 24-hour day and 365-day year provides tangible evidence of Earth's slowing rotation. Similar data comes from tidal rhythmites, sedimentary deposits showing cyclic patterns created by tidal forces. These geological formations record the complex interplay of daily, monthly, and yearly cycles, allowing scientists to reconstruct the Earth-Moon relationship across vast timescales. Rhythmites from the Proterozoic eon, approximately 650 million years ago, suggest the day was only about 22 hours long, with the Moon considerably closer than it is today. Perhaps the most sophisticated ancient timekeeper is found in certain bivalve mollusk shells, which deposit growth rings not just daily but during each tidal cycle. A team of researchers examining a 50-million-year-old clam from the Eocene epoch counted both daily growth bands and semi-daily bands corresponding to high tides. The ratio between these markers allowed them to calculate that the Moon orbited Earth more quickly then, completing its journey in fewer days than it does now. Modern measurements of the Moon's recession rely primarily on the Lunar Laser Ranging Experiment, which has provided continuous data since 1969. Observatories around the world including those at Apache Point in New Mexico and Observatoire de la Côte d'Azur in France, routinely fire powerful laser pulses at the retroreflector arrays placed by Apollo astronauts. These arrays, composed of precisely arranged corner cube reflectors, bounce the light directly back to its source, regardless of the angle of incidence. The round-trip travel time of these light pulses, roughly 2.5 seconds, is measured with extraordinary precision using atomic clocks. Even accounting for atmospheric distortion and the relative motion of Earth and Moon, scientists can determine the exact distance with an accuracy approaching 1 millimeter. This remarkable precision has allowed researchers to confirm the 3.8 centimeter annual recession rate and to detect subtle variations in this rate over time. The Apache Point Observatory, Lunar Laser Ranging Operation, Apollo, has achieved the highest precision in these measurements. Using a 3.5-meter telescope and advanced photon counting technology, Apollo can detect individual photons returning from the Moon, achieving unprecedented accuracy in distance measurements. Complementing these direct measurements, the study of Earth's so-called length of day (LOD) variations provides additional evidence of the ongoing tidal interaction. By analyzing ancient astronomical records, eclipse observations, and even clay tablets from Babylonian astronomers, scientists have reconstructed changes in Earth's rotation rate over historical timescales. These observations align remarkably well with predictions based on the physics of tidal friction. Satellite-based measurements have further enhanced our understanding. Modern geodetic techniques, including very long baseline interferometry, VLBI, global navigation satellite systems, GNSS, and satellite laser ranging, allow scientists to monitor Earth's rotation with microsecond precision, providing real-time data on how tidal forces continue to slow our planet's spin. The orbital evolution of the Earth-Moon system follows principles that govern all celestial mechanics, yet with unique characteristics that make it a fascinating case study in astrophysics. The fundamental equation governing this evolution derives from Newton's law of gravitation, combined with the mathematics of angular momentum conservation. When expressed mathematically, the rate of lunar recession depends on several factors: the masses of Earth and Moon, their separation distance, Earth's rotational speed, and a parameter called the tidal dissipation factor. This last element quantifies how efficiently Earth's rotation energy converts to heat through friction as the tidal bulges move across the planet's surface. The Moon's orbital radius increases proportionally to the sixth power of time, written mathematically as 2 on 6, meaning the recession rate has not been constant throughout history. When the Moon was closer to Earth billions of years ago, the recession rate was significantly higher than the 3.8 centimeters per year we measure today. Computer simulations suggest that immediately after its formation, the Moon may have receded at rates exceeding 1 meter per year. At that time, the Moon would have appeared much larger in Earth's sky, perhaps 3 to 4 times its current apparent size, and Earth's day may have been only 5 to 6 hours long. The acceleration of a body in orbit depends inversely on the cube of its distance from the central mass. This relationship, derived from Kepler's third law, means that as the Moon moves farther from Earth, it experiences less acceleration and therefore orbits more slowly. This is why the Moon's orbital period has increased throughout Earth's history. Tidal forces follow an inverse cube law with distance. They weaken with the cube of the distance between bodies. When the Moon was half its current distance from Earth, tidal forces would have been 8 times stronger, creating massive oceanic tides that may have reached hundreds of meters in height in some coastal configurations. These enormous tides would have significantly accelerated the transfer of angular momentum. The physics of this system creates several interesting thresholds and equilibrium points. One such point is called the synchronous orbit, where a satellite's orbital period matches the rotation period of the central body. Objects beyond this point, like our Moon, tend to recede, while those inside this boundary tend to spiral inward. Another critical threshold is the Roche limit, the minimum distance at which a satellite can remain intact against the tidal forces of its parent body. If the Moon had formed or migrated within this limit, approximately 18,000 kilometers for the Earth-Moon system, it would have been torn apart by Earth's gravitational field, potentially forming rings similar to those around Saturn. The Earth-Moon system is gradually approaching a final equilibrium state called tidal locking or captured rotation. The Moon reached this state billions of years ago, which is why it always presents the same face to Earth. Eventually, Earth will also become tidally locked to the Moon, meaning Earth's rotation period will match the Moon's orbital period, approximately 47 of our current days. At that point, the Moon will appear stationary in Earth's sky, visible only from one hemisphere, and the transfer of angular momentum will cease. However, this final state lies billions of years in the future and may never be reached due to the Sun's evolution into a red giant, which will disrupt the Earth-Moon system long before this equilibrium can be established. The physics governing lunar recession also applies to other planetary systems. Mars-Moon Phobos, for example, orbits so close to the planet that it experiences the opposite effect. It's spiraling inward and will eventually break apart or crash into Mars. Meanwhile, many of Jupiter's and Saturn's moons are also undergoing tidal evolution, creating complex multi-body systems that provide natural laboratories for understanding orbital dynamics. The Earth-Moon system's evolution represents just one example of a universal process occurring throughout the cosmos. Tidal interactions govern the orbital evolution of numerous planetary systems, each with its own unique characteristics and eventual fate. By examining these diverse systems, scientists gain broader insights into the fundamental physics of orbital mechanics. Our celestial neighbor Mercury illustrates the endpoint of tidal locking from the perspective of a planet. Mercury has become tidally locked to the Sun in a 3.2 resonance, meaning it rotates exactly 3 times for every 2 orbits around the Sun. This peculiar arrangement resulted from the same tidal forces driving the Earth-Moon interaction, albeit with the enormous gravitational influence of the Sun playing the dominant role. Venus presents an even more intriguing case. Despite being closer to the Sun than Earth, Venus rotates in the opposite direction, retrograde rotation, and extremely slowly, completing one rotation in 243 Earth days. This bizarre configuration likely resulted from a combination of tidal effects and perhaps a massive impact early in the solar system's history, highlighting how the outcomes of tidal evolution can vary dramatically depending on initial conditions in situ. Stark contrast to the Moon's gradual retreat, Mars's innermost moon Phobos orbits so close to the planet that it experiences the reverse effect. Orbiting below the synchronous altitude, Phobos is slowly spiraling inward at approximately 2 centimeters per year. Within approximately 40 million years, a mere moment in astronomical timescales, Phobos will either disintegrate when it reaches the Roche limit, forming a temporary ring around Mars, or impact the Martian surface. Jupiter's 4 Galilean moons, Io, Europa, Ganymede, and Callisto, demonstrate tidal interactions in a multi-body system. These moons maintain a precise orbital resonance, with Io, Europa, and Ganymede orbiting in a 4.21 ratio. This configuration intensifies tidal heating, particularly in Io, which experiences such extreme tidal flexing that it's the most volcanically active body in the solar system, with hundreds of constantly erupting volcanoes spewing sulfur compounds across its surface. The Saturn system provides yet another variation on tidal interactions. Saturn's rings themselves are likely the remnants of a moon that strayed too close to the planet and was torn apart by tidal forces. Meanwhile, the moon Enceladus exhibits geysers of water vapor erupting from its south pole, a direct result of tidal heating that maintains a subsurface ocean despite the moon's small size and distance from the Sun. Beyond our solar system, tidal interactions play crucial roles in the evolution of exoplanetary systems. Many discovered exoplanets orbit extraordinarily close to their stars, so-called hot Jupiters and hot Neptunes. These planets experience extreme tidal forces thousands of times stronger than those in the Earth-Moon system. Such planets are typically tidally locked, with one hemisphere experiencing perpetual daylight while the other remains in eternal night, creating dramatic temperature differentials that can exceed 1,000 degrees Celsius across the planet. Inau. Binary star systems? Stellar companions can experience similar tidal interactions, often leading to intricate orbital dances and even the transfer of material between stars. The most extreme examples occur in neutron star or black hole binaries, where tidal forces can be so intense that they generate ripples in space-time itself, gravitational waves that scientists have now detected using facilities like LIGO, Laser, Interferometer Gravitational Wave Observatory. The prevalence of these tidal mechanisms across such diverse systems demonstrates that the Moon's gradual retreat from Earth represents a fundamental process in celestial mechanics, one that shapes planetary systems throughout the universe. By studying these varied examples, scientists can better contextualize Earth's place in the cosmic hierarchy and understand the universal principles governing orbital evolution. The Moon's gradual retreat has far-reaching implications for Earth's future. As this cosmic dance continues over the coming billions of years, both Earth and Moon will experience profound changes that will fundamentally alter the conditions on our planet and potentially affect the development of life itself. The most immediate and noticeable effect is the continuing lengthening of Earth's day. The current rate of deceleration, approximately 1.7 milliseconds per century, will compound over geological timescales. In 100 million years, Earth's day will be approximately 25 hours long. Should this process continue uninterrupted for another billion years, a single Earth day would stretch to approximately 47 current hours. This rotational slowing affects Earth's climate systems in subtle but significant ways. Earth's rotation influences global weather patterns, ocean currents, and the distribution of heat across the planet. Computer models suggest that a significantly slower rotation would lead to more extreme seasonal temperature variations and altered atmospheric circulation patterns. Longer days would allow more solar heating of exposed surfaces, while longer nights would permit more extensive cooling, potentially amplifying temperature extremes. The changing day length also affects biological rhythms. Many organisms have evolved circadian rhythms precisely calibrated to Earth's 24-hour day. A significantly altered day length would require evolutionary adaptations across numerous species. Throughout Earth's history, such changes have occurred gradually enough for life to adapt, but they nonetheless represent a persistent evolutionary pressure. As the Moon recedes, its gravitational influence on Earth diminishes proportionally. This decreasing tidal force will gradually reduce the height of ocean tides. Diminished tidal ranges would transform coastal ecosystems, many of which have evolved in response to the rhythmic exposure and submergence created by tidal cycles. Intertidal zones, biologically diverse areas that serve as critical nurseries for marine life, would narrow significantly. Perhaps the most visually striking consequence involves solar eclipses. Currently, a remarkable cosmic coincidence exists. The Sun is approximately 400 times larger than the Moon, but also approximately 400 times more distant, making their apparent sizes in Earth's sky nearly identical. This allows for the spectacular phenomenon of total solar eclipses, where the Moon can precisely block the Sun's disk while allowing the solar corona to remain visible. As the Moon recedes, its apparent size decreases. In approximately 600 million years, the Moon will appear too small to completely cover the Sun, and total solar eclipses will become impossible. Instead, all central solar eclipses will be annular, with the Moon appearing as a dark disk surrounded by a bright ring of sunlight, the so-called ring of fire effect. The Moon also serves as a stabilizing influence on Earth's axial tilt or obliquity. Without the Moon's gravitational influence, computer simulations suggest that Earth's axial tilt would experience chaotic variations, potentially swinging from 0 degrees to over 80 degrees over relatively short astronomical timescales. Such wild variations would create extreme seasonal changes that could render large portions of the planet periodically uninhabitable. As the Moon continues to recede, its stabilizing effect will gradually diminish. While not eliminating this stability entirely, the reduced influence could allow for somewhat larger variations in Earth's axial tilt, potentially leading to more pronounced climate fluctuations over long timescales. The ultimate fate of the Earth-Moon. system depends on the complex interplay between lunar recession and the Sun's evolution. In approximately 5 billion years, the Sun will enter its red giant phase, dramatically expanding and brightening. This solar evolution will likely disrupt the Earth-Moon system before it can reach its final tidal equilibrium state. Models suggest that during this period, solar tides will become increasingly dominant over lunar tides. The expanded Sun may create tidal bulges on Earth that compete with and eventually overwhelm the Moon's influence, potentially reversing the direction of angular momentum transfer and causing the Moon to spiral inward rather than continuing its outward journey. The story of the Moon's formation and gradual retreat provides a window into the violent origins and dynamic evolution of our solar system. Far from being static features of the night sky, the Earth and Moon represent a coupled system in continuous transformation, a process that connects us to both the turbulent birth of our planet and its distant future. The giant impact hypothesis, which proposes that the Moon formed from debris following a collision between Earth and a Mars-sized body called Theia, remains the most widely accepted explanation for the Moon's origin. This cataclysmic event, occurring approximately 4.5 billion years ago, would have temporarily transformed Earth into a molten world surrounded by a disk of superheated rock vapor. Computer simulations of this impact scenario produce a Moon with the correct mass and iron-depleted composition we observe today. The impact hypothesis also explains the similar oxygen isotope ratios found in lunar and terrestrial rocks, a chemical signature indicating a common origin that has been confirmed by analyzing samples returned by Apollo astronauts. This shared history makes the Moon uniquely valuable as a scientific archive. Without plate tectonics or weather to erase its surface features, the Moon preserves a record of the early solar system that has long since been erased on Earth. The lunar surface serves as a time capsule, allowing scientists to reconstruct the history of meteor bombardment, affecting both Earth and Moon over billions of years. The Apollo program's legacy extends far beyond the historic achievement of human lunar landings. The 382 kilograms of lunar samples returned to Earth have been studied for over 50 years, yielding continuous scientific discoveries. Modern analytical techniques applied to these samples have revealed previously undetectable isotopic signatures, providing crucial data about the early solar system's composition and evolution. The Moon's influence on Earth's development may have been even more profound than previously recognized. Recent research suggests that lunar tides may have played a crucial role in the emergence of life on Earth. Strong tidal forces in Earth's early oceans could have created intertidal zones that functioned as natural laboratories for prebiotic chemistry, repeatedly concentrating chemicals during low tide and then mixing them during high tide, potentially catalyzing the formation of the first self-replicating molecules. Throughout human history, the Moon has served as humanity's first calendar, its phases marking the passage of time before written language existed. Lunar calendars formed the basis of timekeeping in numerous ancient civilizations, from Mesopotamia to China. The English word month itself derives from moon, reflecting this deep connection between lunar cycles and human timekeeping. As we contemplate the Moon's gradual retreat, we gain perspective on the immense timescales of cosmic evolution. The processes driving lunar recession operate too slowly for human perception, yet they connect us to both the distant past and far future of our planet. They remind us that the Earth-Moon system we observe today represents just one frame in an ongoing cosmic film that began billions of years ago and will continue long after humanity's time has passed. Modern lunar exploration has entered a renaissance period, with missions from multiple countries investigating the Moon's resources, geology, and potential for supporting human outposts. These efforts may eventually lead to a permanent human presence on the lunar surface, allowing scientists to conduct new experiments on lunar recession and other aspects of the Earth-Moon relationship. The discovery of lunar water ice, particularly in permanently shadowed craters near the poles, has transformed our understanding of the Moon's potential resources. Future lunar inhabitants might extract this ice for drinking water, breathable oxygen, and rocket propellant, enabling sustainable lunar exploration and perhaps even serving as a stepping stone for human expansion throughout the solar system. As we gaze at the moon tonight, we observe a world that is imperceptibly drifting away from us, a reminder that even the most apparently permanent features of our cosmic environment are subject to the relentless forces of physical law. The moon's T-rise recession stands as testament to the dynamic nature of our universe, where nothing remains truly static, and change operates as the only constant across the vastness of cosmic time.